Imagine you are Albert Einstein in 1917. You have just finished General Relativity, the most beautiful theory of gravity ever devised. But there is a problem. Your equations insist that the universe must be dynamic, either expanding or collapsing. However, everyone knows the universe is static and eternal. To fix this, you do something desperate. You add a term to your equations that has no business being there. You call it the cosmological constant, represented by the Greek letter lambda. At the time, lambda was a mathematical fudge factor, a literal placeholder for a repulsive force designed to hold the stars in place against the pull of gravity. When Edwin Hubble later proved the universe was actually expanding, Einstein famously discarded it, calling it his greatest blunder. But today, we know Einstein wasn't wrong to include it. He was only wrong about why it exists. In this video, we are going to look at the math behind why the universe is not just expanding, but flying apart at an accelerating rate. We will define exactly what the cosmological constant is. It is the energy density of the vacuum itself. You will learn how this single number sits inside the Einstein Field Equations, why it creates a push that never dilutes, and why its existence leads to a future where the night sky eventually goes pitch black. This is the story of the constant that defines the beginning, the middle, and the ultimate end of everything, the Great Correction. For a decade, lambda sat in the equations as a stabilizer, a cosmic anchor. But in 1929, the astronomer Edwin Hubble peered through the giant telescope at Mount Wilson and shattered the static model forever. Hubble observed that distant galaxies weren't just moving, they were all rushing away from us. More importantly, he found a precise mathematical relationship. The farther away a galaxy is, the faster it recedes. This is Hubble's law. It is expressed by the formula v equals h sub 0 times d. Here, v is the recession velocity, d is the distance, and h sub 0 is the Hubble constant. The implication was undeniable. The universe was expanding. This discovery turned the world of physics upside down. If the universe is growing, it doesn't need a fudge factor like lambda to keep it from collapsing. Gravity is trying to pull things in, while the initial momentum of the Big Bang is pushing things out. In this new expanding model, Einstein realized his static universe was impossible. He famously struck lambda from his equations, setting its value to 0. For the next 70 years, the cosmological constant was treated as a relic, a ghost of a discarded idea. Physics moved on, assuming the universe was filled only with matter and radiation, and that gravity would eventually slow the expansion down. But as we would eventually learn, setting lambda to 0 was the real mistake. To understand why, we have to look at what happens when you try to measure the deceleration of the cosmos and find acceleration instead. The 1998 plot twist. For decades, the debate wasn't about if the universe's expansion was slowing down, but by how much. Gravity is an attractive force. It should act like a brake on the expansion started by the Big Bang. In 1998, two independent teams of astronomers set out to measure this cosmic deceleration using Type 1a supernovae. These supernovae are known as standard candles. Because they always explode with roughly the same intrinsic brightness, we can use them as cosmic yardsticks. By measuring how bright they appear and how much their light has been stretched, or redshifted, we can map the history of the universe's expansion. The teams expected to see the expansion slowing down under the weight of billions of galaxies. Instead, they found the impossible. The distant supernovae were much dimmer than the deceleration models predicted. This meant they were much farther away than they should have been. The conclusion was inescapable. The expansion of the universe isn't slowing down. It is accelerating. Something is acting like a cosmic gas pedal, pushing galaxies apart faster and faster as time goes on. This discovery brought Einstein's discarded constant, lambda, screaming back from the dead. But this time, it wasn't a fudge factor to keep the universe still. It was the mathematical description of dark energy, a mysterious pressure that makes up nearly 70% of everything in existence. To understand how a single constant can push the entire universe, we have to look at the math Einstein tried to hide. The anatomy of the equation. To understand why the universe is accelerating, we have to look at the master script of gravity, the Einstein Field Equations. On one side, we have the geometry of spacetime. On the other, we have the energy and matter within it. In its simplest form, the equation tells us that matter tells space how to curve, and space tells matter how to move. But look closely at the left side. Nestled next to the terms for curvature, we find our constant. The full expression is g sub mu nu plus lambda times g sub mu nu equals 8 pi g over c to the fourth power times t sub mu nu. Let's break this down. G sub mu nu represents the curvature of spacetime. T sub mu nu represents the energy and momentum of matter. But lambda is different. Because it is multiplied by the metric tensor, g sub mu nu, it isn't attached to a specific star or a galaxy. It is a property of the coordinate system itself. It is a property of space. In the language of math, this means that even if you remove all the matter, even if you set the energy-momentum tensor to 0, the equation doesn't go to 0. If lambda is positive, space still has a curvature or a tension inherent to it. Think of it like this. Matter and radiation are things that live in the universe. They dilute as the universe expands. But the cosmological constant is a part of the fabric of the universe. As the universe expands and creates more space, it creates more lambda. This is the mathematical reason why it doesn't just push, it accelerates. The more space there is, the more push there is, which creates more space in an endless cosmic feedback loop, the vacuum catastrophe. We have seen that lambda represents the energy of empty space. But where does this energy actually come from? To find out, we have to zoom in, past the atoms, past the subatomic particles, down to the quantum scale. According to quantum field theory, empty space is never truly empty. It is a bubbling sea of virtual particles, constantly popping in and out of existence. These fluctuations should contribute to the energy density of the vacuum. When physicists use the tools of quantum mechanics to calculate how much energy this nothingness should contain, they get a number. Then, they compare that number to the actual observed value of the cosmological constant we see in our telescopes. The result is the most famous failure in the history of science. The theoretical prediction is larger than the observed value by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. This discrepancy is known as the vacuum catastrophe. It is the largest mismatch between theory and observation in all of physics. If the quantum prediction were true, the push of the vacuum would have been so violent that atoms could never have formed. The universe would have been ripped apart in its first trillionth of a second. This tells us that we are missing something fundamental. We have the math of the very large, general relativity, and the math of the very small, quantum mechanics. Both work perfectly in their own realms, but when it comes to the cosmological constant, they disagree on a scale that is literally astronomical. Solving this mismatch is the holy grail of modern physics. It is the key to a theory of everything. The cosmic tug-of-war. To understand the fate of the universe, we have to look at the ratio between two competing densities, matter and lambda. Physicists use the Greek letter omega to describe these densities. Omega sub m represents all the matter in the universe, stars, gas, and the mysterious dark matter. Matter wants to pull things together. Omega sub lambda represents the cosmological constant. Lambda wants to push things apart. In the early universe, matter was packed tightly together. Because the density of matter was so high, gravity was the dominant force. For the first 9 billion years, the expansion of the universe was actually slowing down. Gravity was winning the tug-of-war. But as the universe expanded, the density of matter dropped. Matter dilutes. If you double the volume of space, the density of matter is cut in half. Lambda, however, is different. Because it is a property of space itself, its density remains constant. It does not dilute. Around 5 billion years ago, the universe reached a tipping point. The density of matter dropped just enough that it was overtaken by the constant, unchanging push of lambda. This is the moment the tug-of-war shifted. The brake was released, and the gas pedal took over. Today, we live in a universe where omega sub lambda makes up about 70% of the total energy density, while matter makes up only 30%. We have entered the lambda-dominated era. The balance has been tipped, and according to the math, there is no turning back. The more space lambda creates, the more dominant it becomes, and the faster the galaxies retreat into the distance. The physics of nothing. In our daily lives, pressure usually pushes outward, like air inside a balloon. But in the strange world of general relativity, the cosmological constant acts through something called negative pressure. To understand this, think about the energy of the vacuum. As we've seen, lambda is a constant energy density. If you expand a volume of space, you haven't stretched the energy thin. You have simply created more space, and therefore, more total energy. In thermodynamics, if you have a substance that maintains a constant density even as it expands, it must have a negative pressure. While ordinary matter has positive pressure and a gravitational pull that slows things down, the negative pressure of the cosmological constant creates a gravitational repulsion. It is a literal anti-gravity effect built into the vacuum itself. This is why lambda is so much more powerful than the momentum of the Big Bang. A normal explosion loses energy and slows down as it spreads out. But the expansion driven by the cosmological constant is self-sustaining. Because lambda doesn't dilute, the push per cubic meter stays exactly the same, no matter how large the universe gets. But because there are more and more cubic meters of space being created every second, the total volume of push grows exponentially. It is the only thing in the universe that gets more powerful the more it is used. It is the ultimate free lunch, and it is currently dictating the movement of every galaxy in the cosmos. The Big Freeze. If the cosmological constant remains constant, as the math suggests, we can predict the final chapter of the universe with haunting precision. This is the Big Freeze. As the expansion continues to accelerate, galaxies are being pushed away from us faster than the speed of light. Now, this doesn't violate relativity because the galaxies aren't moving through space that fast. It is the space between us that is stretching. Eventually, every galaxy outside our local neighborhood will pass over a cosmological horizon. Once a galaxy crosses this line, the light it emits can never reach us again. One by one, the lights of the universe will go out. In about 100 billion years, the Milky Way will be an island universe, surrounded by a void so vast that no telescope, no matter how powerful, will be able to see another galaxy. Any astronomers living then will look at a pitch-black sky and conclude that they are alone in a cold, static, and empty dark. The cosmological constant is the ultimate architect of loneliness. It is the number that ensures the universe doesn't just end with a bang or a whimper, but with a slow, inevitable fade into nothingness. Einstein called it his greatest blunder. But in the end, lambda might be his most profound legacy, the single constant that explains why we are here and why, eventually, everything we see will disappear.